All right, recording's rolling. It's Wednesday, April 5th. We're going to take a couple of days to do something a little bit different from AP. Now, some context. A few years back, AP changed their exam and they bumped a few topics that have been on it forever. One of those topics is electricity and DC circuits. Actually, there was a couple of units that involved they bumped. Now, I learned this back in high school. I know a lot of you guys like this will be the only chance that the only opportunity you have to learn this, and I think this is really good to learn for a number of reasons that I'll tell you as we're going. Right, it's good to have this knowledge, right? How electricity and circuits work. So we're going to take today and tomorrow to do this because I really do think it's worth the time. It's important to learn this. After the AP exam, there's other physics stuff that I want to cover with you guys too, but that'll be such limited time anyway. So we're going to stay today and tomorrow. Uh, in terms of AP, there's really only one topic we have to still review. That's Unit 7, which is rotational dynamics, which is a pretty hefty topic, right? Because it's kind of like everything we've learned times two, right? Because everything in linear sense now how is a rotational type component. So I did go ahead and open up Unit 7 multiple choice questions part B on AP Classroom. This might be the last thing have you guys done AP Classroom other than the practice exam. There's still one more practice exam I got for you guys. So I have a tentative due date this coming Wednesday. I might bump that, but I have to plan this weekend. So anyway, if you guys want to dig in there and start looking at those, you can. All right. So you guys okay with what we're doing? All right. So all right. I got here, I'll take you guys through these posters that are hanging around my ceiling. I've been doing electricity with my other classes for a few weeks now, but I'm going to try to condense this down to just a couple of days. Okay? Also on your desk is this page of circuits. There's circuits on the side and circuits on the side. So I'll go over this page with you guys in time. All right, so some variables you see involving electricity. Right, so you can have just a static charge we can measure in coulombs. Right, now I have a demo example for you guys. So let's say, have you guys ever done this for a balloon goes your hair? Right, it charges up the balloon, right? So there's a transfer of electrons from your hair onto the latex of the balloon. So now the balloon's like negative charge, right? And so your hair would be left positive charge, right? Then you can like stick the balloon. Okay, oh yeah, it's working really well today, right? It's better than others, but there you go. It's like sticking to the ball, right? Right, so that balloon has a charge on it, right? And then charges will actually attract, right? So if you have either opposite charges or like something that's charged and something that's neutral, like you see right there, okay? So here, we're gonna get that. So you can measure this coulombs. Okay? Ooh, how about another demo type for you guys? I got this Van de Graaff generator, Van de Graaff. So I'll have this open tomorrow too. So if you guys don't get a chance to get your hands on this today, maybe tomorrow. Right. What we got? Right. Same type thing going on here. I got this belt. There's a wire brush inside it's running against. So there's a transfer of electrons, right, which is leaving this positively charged up here. And you might be able to see. Is it? Okay, actually, I can feel it a little bit. I can feel a little bit of static charge. Some days it works better than others. Florida, it's hard to get it to work too well because there's a lot of humidity. But I will leave this here tomorrow too. One thing that's fun to do. Now we can't quite do this now because it's not working super well today. But sometimes you can like get a chain of students, have them stay on their desk. Because now stay on desk is important because if electricity wants to run to the ground if it can. So, but if you get a whole chain of students like stay on their desk, you can make a ring and like send a shock wave around, so you can feel that too. So possibly tomorrow might be a good opportunity. I do have a video demo of this too. I'll put a few minutes here. Right, so if you get a charge to flow, they're called current. In electricity, it's always capital I is used to represent current, and that's measured in amps, amperes, which is coulomb per second. Okay? Now, why would a current flow? Why would there be a flow of electricity? There's a flow of electricity if there's a potential difference. And you can measure that in volts, right? It's called voltage, right? Symbols for that. Volts is joules per coulomb, so it's like energy per unit charge. Right? So a battery has a voltage, has a potential difference, right? And it's, okay, now you need the rest of the circuit to make this work too. So to get the electricity to flow, right? So I've got a quick demo here. Right? So 9-volt battery, and boom, there you go, it lights up. So that's a basic circuit right there. Right? So 9 volts in this battery. Do you guys know how many volts a AA? It's like 1.5. Right? Actually, it's true for like C and D cell batteries too. They're 1.5 volts. It has to do with the chemicals inside them. Now Do you want there to be a resistor in your series? Resistance is measured in ohms, right? So here, give you guys kind of a counterexample. Have any of you guys ever taken, say, a paperclip and unwound it and attached the positive directly to the negative of the battery? Okay, what does it do? Gets real hot real fast, right? You probably start a fire with it. It also drains the battery really fast, right? That's called a short circuit. Right? If you have none of this going on, if you have no resistance, no resistor, right, it shorts out. So the electricity just runs really fast and it just drains the battery really fast. And that's not ideally what you want, right? And so you have decent circuits. Uh, Power in watts, right? So you plug in a light bulb. Usually, the light bulb says how many watts it is. Now that's related to a bunch of other things too, like what sockets plugged into, right? But yeah, so could be joules per second, but this one you guys have seen last semester, right? So you're familiar with this one. So you don't actually have to have like amps or coulombs or anything to make watts, right? It's just joules per second energy per time. But now this is connected to these other variables too. I'll show you guys later Joule's law. Right? These couple lines down here in green, usually save for a later day, but you can also put other things on circuits too, capacitors and inductors. They have different functions, so they'll do different things. But we're gonna probably mostly focus on this yellow stuff. I know we only got a couple days of trying to condense things quite a bit. Okay. So Coulomb's law. Right, so if you have two charges, they can attract or repel. Does this look a lot like universal gravitation? You guys remember gravitation was like G(m)(m) over r squared? Well, this is k(q)(q) over distance squared, right? So really similar type of concept. Okay? Now it's between 2 point charges. Now one difference between this and gravitation is this can also repel. So if I had like positive positive, that would repel, or negative negative would also repel, right? Now here I drew opposite charges, which would be an attraction, right? That's magnitude of the force there. There's the electrostatic constant. Interesting to note, this is a huge number. This is like a billion. 10 to the 9 is like a billion, right? Versus universal gravitation is like 10 to the negative 11. So this is a much, much, much stronger force, right? You see that right here. So I drop my pen and it comes to a dead stop, right? Well, gravity's pulling it down, but there's an electrostatic force, the electrons on the surface and electrons in the pin that are repelling. So this is a much stronger force considered gravity. All right. Ohm's law, super important in electricity. Right, we're going to navigate this quite a bit today. So how much current actually flows? Well, it's what's the voltage divided by what's the resistance. So if I know this is 9 volts, for example, right? And I know the resistance of this, let's call it 2 ohms. It's pretty close to 2 ohms, right? Connect that, boom, right? How much current's flowing? Well, 9 volts on 2 ohms, that'd be like 4.5 amps. Boom, there you go. Flashlight schematic. So that's kind of what I just built, right? I just kind of built that. That's a switch right there, symbol for switch. Right? Resistors, the symbol is that jaggedy symbol. So this could be an example of a resistor. Right? Not all resistors are light bulbs, but bulbs are examples of resistors. Now, when I first learned electricity myself back in high school, it did take me a few weeks for this idea to click. I thought it was confusing for a long time. And when it clicks, right? But you got to kind of spend time with it and work with it, think about it deeply. When I was taught this analogy, that's where everything really came together. Because what's like voltage in volts and current in amps, like what's going on there? So when you see voltage, think pressure. So this battery is kind of like the pump, like trying to push electricity through, right? This guy's 9 volts, this guy's 1.5 volts. So this guy has like a lot more pressure sort of thing. And it's really voltage, electric potential. When you see resistance, think of it like a crimp in the pipe, right? So reciprocal of area sort of, right? It's reciprocal of conductance is what it is too. And then how much current actually flows, think like flow rate, like gallons per minute, cubic meters per second. Right? Again, this is just an analogy, but it works pretty well. I actually have my other students do this lab today. Right? What's the resistance in a wire, like from end to end? Well, the longer the wire, the more resistance. That makes sense. Right? How about this? The fatter the wire, the less resistance. All right, so inverse relationship there. Right? And finally, resistivity is a material property. Do you think an aluminum wire and a copper wire transmit electricity differently? Right. So that's built into this material property. Right? If you traditional resistors and circuits usually look like this. They have these colored bands, and you can read the color bands. It tells you exactly how much resistance it is. So this one got brown, green, red, and then a gap, and then it's gold band. So I go 1, 5. Now red is 2, but in this context, it's like 10 to the power of 2, right? So it's like 1500. So 1500 ohms, and then the gold band tells you plus or minus 5%. Joule's law. And so how much power actually flows through, say, like the system right here, right? It has like how bright as this bulb, sort of, you can think of that. It's related to that. Like, what's the rate that this battery is being drained? Right? That's power measured in watts, right? So what would that be? Oh, here's three perspectives on it. They all tell you the same results. So depending on what information you have, one of these might be more convenient than the other. So you could do current times voltage. That's a good way to do it. You could do current squared times resistance. You could do voltage squared divided by resistance. They'll all tell you the same thing. So like if I know this is 9 volts and this is 2 ohms, I could go 9 squared is 81 divided by 2. Right, so it would be about 40 watts. So boom, that's like about 40 watts right there. Okay. Right, here's back to that analogy with like pumping water. So your battery's like a pump. It's providing like some pressure, think like that, voltage pressure. Okay? And then this water wheel could turn at some rate, could deliver some amount of power, right? Energy per time, that's what power is, right? Joules per second is what watts. So current, what here, this really connects back to this one here. Power is current times voltage. That's what that says, current times voltage, right? Oh, that's what it says right here, current times voltage. And that's like a flow rate times the pressure, sorry, right? And these units actually work out exactly too. So this is a really good analogy. All right. Um, here, okay, so we're starting to build up a circuit. I got my battery here, my voltage source, battery. Okay? And what if you had like 3 resistors in a row like this? Here, let me wire this up. What is the total resistance? Got some examples ready to go. All right. So here. Oh, gotta plug this in. Is one of these dead? One of these might be dead. That one. Yeah, I think this middle guy's dead. Here, let me ooh, here, let's try these. All right. Ooh, so they're on, but notice they're really dim. You guys see how they're really dim? Right? Compared to just one, might be really, really bright, right? Oh, I should tell you guys too, this is a cell phone charger. This is 5 volts. I've got a 5-volt cell phone charger right here, 5 volts. Right? So there's 5 volts across these leads, which is about half of this guy, which is 9 volts, right? It's got 5 volts going on right here. Right? But you saw they're really dim. That might be an indication that maybe the resistance is building up more and more and more. So if you put resistors in series like this, it's called in series where they're like in a row, right? Then the resistance builds up more and more, and all you have to do very simply is add them together. Right? Here, think about this. I'm going to use a traffic analogy. Suppose this battery here represents a parking garage, right? And there's a bunch of cars that want to drive around town, right? And so you're looking at, okay, so I'm going to make a trip around. Now you have to have the positive connected to the negative terminal battery to make a complete circuit. And you see like, see a red light there, red light there, red light there. Well, the more red lights, the more resistance is in your trip, right? So maybe less traffic's gonna flow. That'd be like less current. Versus if you see resistors like this, like wired, like rungs of a ladder, this is called in parallel. And the total resistance actually decreases when you wire them in parallel. Here's the math, how you do this. Okay. Let me show you guys what this looks like. So I got these 3 guys are all tied in parallel because their leads are all tied together. So it's like boom, boom, boom. It's like that. Their all leads are tied together. Now remember when I had 3 in series, like one after another, they were all really dim. Like they lighted up, but they were really dim. What's 3 in parallel gonna look like? Ooh, you guys see how bright that is? Whoa, they're crazy bright, right? Like a single bulb was just as bright as each one of these was connected in parallel. Right? So ways to think about this. There's this one that was dead. Let me check when it gets guy. No, that one's working. Something's dead in that one. I gotta fix that later. All right. Few ways to think about this. One way to think about this is that each of these has the same voltage drop going across it. Like if this is a 9-volt battery, for example, 9 volts, every single one of these feels 9 volts going across it, which was not actually true for back here. If this is 9 volts, it actually drops a little bit at a time, drops 3 volts, 3 volts, 3 volts, right? So the voltage will continually drop, right? But here it's like the same voltage going across, right? Another way to think of this, let me break out my traffic analogy, right? So what if you just had this, right? So you leave this parking garage, drive around town, there's one red light, right? But then new roads are starting to be built. And even though that also means like more red lights, so you say, hey, there's more red lights. Is that more resistance? That's actually not, because it's like more opportunities to choose roads to drive on, right? So now there's like more incentive to drive around. So now there's going to be even more traffic, right? Because there's paths they can choose, right? So that is in parallel. So it's like more current in amps from the battery. Now, here's the math of this. If you add the reciprocals together and then take the reciprocal of that, you get the total resistance. Let's do a quick example. What if each one of these guys is 2 ohms? So 1/2 plus 1/2 plus 1/2, that's half plus half, that's 3 halves. Then you take the reciprocal of that, that'd be 2/3. So this battery feels like it's pushing through 2/3 of an ohm. That's like 0.67 ohms, even though each one of these individually is 2 ohms, right? Okay. Now, if you only work with 2 or 2 at a time, you can more simply do just product over sum. But you can't do like 3 at a time like that. So you can't do multiply 3 things divided by plus 3 things. No. Or you only do 2 at a time for product over sum. It's a simplification. You can try that here. If you do this to get a common denominator, get RB over RA over B plus RA over RA RB. Right? And then take the reciprocal of both sides, it ends up being exactly that right there. Right? So if you have 2 at a time. Right now, one reason I should tell you guys, I guess it's a good time. One reason that I think electricity and circuits are really good to know is not just for electricity and circuits. All these analogies that I've been telling you guys about like water through a pipe or traffic through a city also apply to, it's like the same math going on here. Okay? Like here's a similar type example. What if you had 3 guys painting a fence, right? And this is a common example I use all the time for electricity, right? And each individual guy would take like some time to paint the fence. Like let's say this guy takes 10 hours to paint the fence all by himself, and this guy 10 hours, and this guy 10 hours, right? Well, what if they team up and make a 3-man team? Does it take them more time or less time to paint the fence? Less time overall. In fact, the math is exactly the same as this. So you do 1/10 plus 1/10 plus 1/10. That's 3/10. Take the reciprocal, boom, 10/3. That's like 3.33 hours. Oh, that makes sense, doesn't it? I mean, if they were all the same 3-man team, it should be a third of the time that it would be for each individually. Wouldn't that make sense? Yeah. Okay. I see that. If you're building a water pipe system around town, you're an engineer. Think about these DC circuits because same thing about how is pressure and current divert and drop. Right? If you're constructing a traffic system, you're a traffic engineer. Think, how do I want to build roads and red lights, and what's like the demand for traffic, and how's the traffic going to flow? If you're just putting together a huge project, just any project, like, and you got to manage, okay, well, we got to do this step first, and we got to do these 2 steps in parallel together, and then after that, we can in series add this other step. And you want to manage how much time does it take to complete a huge, like, multi-million-dollar project. This whole circuits analogy can help you figure that out too, right? Which is a great segue to this one here, Kirchhoff's rules. Now, I did go back and redesign this poster. This does need an update. Kirchhoff really only had 2 rules. There's only 2 rules. There's what's called the loop rule, which is this right here. And I know this is split like series and parallel examples, but this loop rule really applies to any loop. So I got rid of that row series because this applies just in general. And his other rule is called the junction rule, which is this right here, which actually would apply to something like only this one, right? Okay, so the loop rule says if you identify any loop, the voltage has to sum to 0. So for example, this might pump up 9 volts, and then it might drop 6 volts here and 3 volts here. Right, the up 9, down 6, down 3, right? So that could be a loop. Right? But here's a loop here, here's a loop here, here's a loop here, and that would always be true, right? Now here, you'd be going against the current one way and with the current the other way. So it's the same voltage drop across each one, right? Now this junction rule says that if the current splits, it has to be conserved, right? So it has to do like a conservation of charge thing. Loop rule is like conservation of energy. This one's like conservation of charge. So if I got like 9 amps coming around, maybe it splits 6 amps and 3 amps, but then it comes back together like 6 and 3 make 9 again, right? That's how current works. Right? Now there are a bunch of consequences that fall out of this. Again, I redesigned this poster to, this is right. If you have strictly a series circuit, the current has to be the same everywhere, right? So the same number of amps through this one is this one, even if they're different resistances. That's okay. It's the same current, same number of amps, right, along that street. Right? However many cars go through this red light, same number of cars that go through that red light. If you have a strictly parallel setup, then the voltage drop has to be the same across these guys. That's really consistent with the loop rule. That's like the loop rule applied to like parallel circuit. Right? So if this is 9 volts, this is going to be a 9 volt drop and a 9 volt drop, right? It down to 0. Then, right? Even if there are different resistances and different currents going through them, that's okay. It's the same voltage drop. Right? Now, how exactly does the voltage drop one at a time in series? So it's actually going to be proportional to each resistor. So if this resistor is like 1 ohm and this resistor is 2 ohms, right? Again, it's the same current going through them, but let's say it's a 9 volt battery. Right? Then however many volts drop, okay, 1 to 2, that's 1 to 2 ratio, right? Hey, wouldn't this be like a third of the total resistance? This is 2/3 of the total resistance. That's like that fraction right there, right? So if it's a 9 volt battery, then I'd have 3 volts drop here and the other 6 volts drop here, right? That's exactly what this says. So each voltage drop is proportional to that resistor. Okay, does that make sense? Okay. Now, in a parallel setup, uh, of course, the voltage drop has to be the same across each one. We said that already. Okay. But how does the current split, right? Because again, in a series, the current's the same everywhere. But in parallel, the current's going to split. Hey, where do you think more current would go? Through 1 ohm or through 2 ohms? How about through 1 ohm, right? Like path of least resistance. Right? Like if you saw 1 red light here and 2 red lights here and drive around town, probably most of the traffic's going to go along 1 red light, right? But after a while, that traffic builds up, and then there's some incentive to choose the other one. So maybe a little bit of traffic trickles the other way. In fact, that's also proportional. But now here's now this looks a little tricky at the outset, but it makes sense if you think about it. The amount of traffic that goes along branch A is actually proportional to the other resistor, right? Because of that reason. So if this is 1 ohm and 2 ohms, let's say we got 9 amps, for example. So 9 amps coming around, right? This guy's 1 ohm, this guy's 2 ohms. Well, you do 2/3 of the traffic actually goes along the least resistance. So the 2/3 of 9 is 6. So 6 amps actually go through the 1 ohm. And the other 3 amps go through the 2 ohms, right? You guys see it? So these subscripts are backwards. This is resistor B and current through branch A, right? And vice versa. Right? Up here, total current. Okay. So again, giving you guys a real fast crash course of all this stuff today, and we'll do a little bit of practice with circuits, but this is stuff that, like anything in this class, you have to sit down and think pretty deeply about. But I'll fix that. Right, breadboard, so you can plug in resistors and voltage sources, and also capacitors and inductors, and make all different things. I've seen people build little mini robots out of these. If you know how to wire stuff up. Now, what's good to know is on the backside how everything's wired. So like these 5 are connected, these 5 are connected. Right? There are these some kinds called rails or buses that run along the entire outside here, right? Run along the entire outside. So if you know what's going on in the back, just look at the front, because the front just looks like a bunch of holes. But if you know what's going on behind the scenes, you can know how to wire things up. Like what I would not want to do is there's a single resistor. What? Get this guy. Right. Is plug in something like here and here. That would be completely pointless because there would be this metal strip underneath it that has basically 0 resistance. So this would always be shorted out and it would never turn on. Now, if I bridge this gap here like this, right now the electricity is forced to flow through that resistor. Okay. All right. All right. So take a lot of those ideas that I've been telling you guys about, and you can put also all together with, say, a waterfall analogy. I like this waterfall analogy a lot. Okay. So let's say I got 9-volt battery, so 9 volts here, and some resistors in series. Okay. Well, the voltage is going to drop a little bit at a time. Maybe it drops 3 volts, 3 volts, and 3 volts. But remember, voltage is kind of like pressure. Hey, do you think if you have a really deep dam, the deeper the dam, the more the pressure? Right? So pumping up 9 volts is kind of like having like a 9-meter tall cliff, right? And it dropped, like 3 volts, 3 volts, 3 volts. You see that? It's going to drop like that. But the current, remember, has to be the same everywhere. Right? That's what I was telling you guys with current's the same everywhere. Right? So there's only one stream for the current to go. So another example. What if you had 3 in parallel? Remember, this is where they're all bright. And one reason they're all bright, one way to think about it is they all have the same voltage drop going across them. If it's 9 volts up, it's 9 volts down, right? You see 9-volt drop here, 9-volt drop here, 9-volt drop here, right? But the current's going to split, right? Now, if they're all the same resistance, then it will split equally, right? You have 3 currents that are all the same number of amps. But if you have like a huge resistor here, maybe a couple of tiny resistors, then the huge resistor is probably going to be a little like skinny waterfall, a little bit of current. Right? In the tiny resistors, maybe there's going to be like big wide waterfalls, like a lot of current, right? So, okay. And you follow those Kirchhoff rules and the things that come out of the rules that drop out of those, and figure out exactly how it's going to. Now, you can get something more complicated. Like what if you had something that looks like this, where there's a combination of series and parallel. Okay. Well, now these are getting a bit more complicated, right? So you got to navigate like inside the circuit, what's going on. Right? So I can tell you guys that this one would be really bright because it's getting the full voltage drop. That's like here, the full voltage drop. And these guys would be dimmer because the current splits and then it splits again, right? And then it comes back together here at the bottom. Okay, you see that? Waterfall on. So yeah, the current, it's like amps, however many amps are going this way, and this way. And the height change, it's like a pressure difference. That's like a voltage drop. Right, you guys good? All right. Ooh, I do have a multimeter here. So get this Oh, I forgot to bring my alligator clips. I do have some, but here, maybe, so we can put this together here. Show you guys how to work this thing. Let's just do a real basic one, right? So how do you measure how many volts are dropping at any point in the circuit and how many amps are flowing through any point in the circuit? Okay. Let me start with amps. Now, amps, so voltmeter, so this is a multimeter, wait, so it can measure like different things, different functions. Okay, I'm gonna take this guy, pop it out over here, leave one in COM, giving you guys a huge crash, really fast crash course here. So show you guys how this works, right? Flip this one over to measure like amps, right? And then now amps is like measuring current. So you have to break open your circuit and connect the ammeter function in series with your circuit and force it to flow through the multimeter. So let's see what that is. If I attach the red to the red side and the black side, now this bulb's about to light up. Watch it light up. Boom. Okay. And do you guys see 2 amps? You guys see 2 point something amps? You guys see that? So then you got 2 amps flowing. Okay. Now, if you want to measure voltage drop, you actually have to measure it in parallel because you're measuring a potential difference. What's the potential difference across this bulb? Okay. And for that, I have to actually make the full circuit. Full circuit right here. Okay. Flip this one over to volts. Okay. Also switch this out. Put it back in where it can measure volts. Okay. And then connect my leads across. And it's going to measure the voltage drop. That voltage drop is, remember I told you guys I had a cell phone battery here, and this is the cell phone charger is like 5 volts. Look at that, that's almost 5 volts, isn't it? Okay. Yeah, plus or minus a little bit. It's almost 5 volts. Guess that. So I have 5 volts. I had 2 amps. Let's go way back to Ohm's law and put this all together. So Ohm's law. Right? You guys saw 2 amps. You guys saw 5 volts. 2 times cross multiply resistance, divide this down. So 5 over 2, that's like what, 2.5. So that resistor is about 2.5 ohms. I said that bulb was about 2 ohms, so that probably fits in that window, right? They're all slightly different, but right about 2 ohms. Ooh, a hot bulb right there. All right. You guys good so far? All right. All right. Let's do. What are some other things you can put on a circuit? Right? Because here's your voltage source. That's like your battery. 2 parallel lines, one longer than the other. Okay? A fuse is something that, like, if there's too much current surging through at one time, it'll blow the fuse, and that'll immediately open the circuit and stop the current flow. Right? Which is there for safety reasons. Right? Let's say you step out of the shower and you go to plug in something, and you're accidentally touching the that metal bit as you're plugging it in, so that you're making contact with it, and then the current wants to flow through you, right? Which could give you a pretty good shock, right? That'd be bad, right? So if the current like starts flowing through really fast, then this will blow, and then it'll open the circuit. Okay? So you want to connect this in series, exactly as shown there. Right? Here's your resistor. That's like these bulbs. So that's most of what we care about here. Right? Now there's other things you can put on a circuit. So here's a couple of them. Inductor, which is a coil of wires, which actually creates a magnetic field, which you can do a lot of interesting things with. Right? It's actually involved in electricity generation. If you run this past another magnet, like a permanent magnet, it will generate a voltage itself. That's how electricity is generated. It'll also cause current to lag. So if I should have thrown a switch on here too, but if you had like, I think I had a flashlight schematic that had a switch shown on it. Where's my, there it is. Here's a switch. Here's a switch. You can open it, it will turn off the electricity, right? And then close it, it will create a complete circuit. Okay. So if you hit an on switch to close the circuit, then it'll take a while for the current to build up if one of these guys is in here. And then you hit the off switch, then maybe this bulb will like slowly dim out. Right? A capacitor is like 2 parallel plates, which looks a lot like what's drawn here, right? And this can store energy in an electric field, and it causes voltage to lag. Right? So the volts take a while to build up or dissipate if one of these guys is in here. Right? This acts kind of like a battery in a sense. We actually have a Faraday flashlight here. Jump it a little bit here, but it's got a magnet, coil wires. If you force the magnet past a coil wires, it will generate a voltage. And there is not a battery in this light, but there is a capacitor, which is one of these guys. Right? So I can store the energy that way. Second side, a battery. The battery has chemicals that have a potential difference between them. So this is just one design of a battery. It's not the only design, but you could do manganese dioxide for the cathode, and zinc for the anode, right? So separated by this electrolyte, potassium hydroxide. And then if you connect these leads to each other, then you get current to flow. And then there will be a chemical reaction. These chemicals will change as it drains the battery, but there's a potential difference of like 1.5 volts between those two. Okay. Oh, here's your capacitor. Uh, okay, so here's so charge per voltage causes voltage lag, energy you can store inside the capacitor. And interestingly, if you have these on your circuit, they actually follow the opposite rules of resistors. So if they're in series, you actually do product over sum, like a team people painting a fence. And if they're in parallel, you actually add them up. So here's inductors, just this coil of wires. We're showing you guys. Here's the inductance. Now, inductance has to do with, what is this? Voltage over a rate change of current. That's change of current over change of time. Okay? And it causes current to lag. Ooh, look at that. Here's energy you can store in the inductor. Okay. And inductors follow the same rules as resistors. So in series, you just have them up. Parallel, you do product over sum. But remember, well, product over sum if you only have two at a time. Okay? Right-hand rule for electricity. So if you have any two of these, then the third one can pop up like almost by magic. Here, to guys do some examples. So you guys know F is a force. You can measure in newtons, right? I is electric current measured in amps. What do you guys think B is? It's a magnetic field measured in Tesla. I should throw that on a poster somewhere too. Magnetic field measured in Tesla. And if you have a really long wire, the longer the wire, the more force you can get to. Right? So if you have any two of these, you can get the third one. I'll take you guys through all three examples. If you force a current into a loop, right? Well, that's like an inductor, right? That will actually create a magnetic field. It'd be like an electromagnet, right? If you run a current by a magnetic field, right? So if I had a wire that had some current running through it next to a permanent magnetic field, it would actually feel a push. It would push it like perpendicular. And that is the principle behind motors. That's how you build a motor. Right? So you run electric current past a magnet that can like cause a ceiling fan to turn. Right? And the third thing you can do is you can force a magnet past a wire, which will generate a voltage, which will generate a current. Okay? And that's what a generator is. Right? So how do power plants work? Well, most of them involve say like steam turning a turbine, and that turbine forces a wire past a magnet or magnet past a wire, right? And that will create a current. Okay? By the way, that's called Faraday's law. So the voltage that is induced by this process of the magnet past the wire is, what is this? It's the rate change in flux. And what is flux? So flux is magnetic field times area. So if you have a magnet, there's magnetic field lines, right? North to south. So B is magnetic field, right? And you're moving that in and out of a coil of wires, right? Then the rate change of that flux, right, as that magnet moves past those wires. So B times A, B times A. The rate change of that times the number of coils. So if you have like 2 coils and then up that to 10, right, then you get more and more voltage. I usually use V for voltage or delta V for like potential difference voltage. Some textbooks use epsilon, so I would just went ahead and through that here too, because sometimes some textbooks you see that epsilon for voltage. Okay. So generator and motor, if you've been following, are really like two sides of the same coin. They're like opposite processes, but they're really like the same type device. Okay? So say you had so a generator will take mechanical energy and convert that into electric energy. Because if you can get a wire to move past a magnet, right, then that'll create a voltage which will create a current. Okay? Then on the other end of the spectrum, if you have a wire running past a magnet and suddenly there's a current surging through it, then it will start to move itself, and that will convert back to mechanical energy, electrical to mechanical energy. Okay? Could be like a ceiling fan going on. Inductive coupling. You can transfer energy wirelessly. I do have demos for all these too, so again, trying to condense all the stuff quite a bit. But if you have, say, like a coil wires here and coil wires here that are not touching, so this red wire and this green wire, there's no contact between these two, okay? Then remember that as current's flowing through this coil, which is like an inductor, it will generate a magnetic field. Do you guys think this one would pick up that magnetic field? Yeah. And then that will in turn generate its own current. So anytime you see wireless transfer, like wireless charging or wireless transfer, right, there's usually some version of this going on. Now the voltage will transfer proportional to the number of coils. So I have a large number of coils there and a small number of coils there. That means that from left to right, if that's where we're going left to right, this would step down the voltage. Like if this is half the coils of this, then it'd be half the voltage, right? So, right. So number of coils saying how much voltage. But what happens at the same time is the current actually does the opposite thing. So I might have a low current here and a high current here, okay? Which is actually consistent with Joule's law. You guys remember power is current times voltage. Well, here, I showed you guys that earlier. So power is a rate of energy, and energy is conserved. So the power should be the same on both sides as long as it's all happening simultaneously. So if I'm dropping the voltage left to right, then I'm also increasing the current at the same time. Okay? And kind of an analogy for this, because these are used all over the place in the actual electric grid. So when you see utility lines are actually alternating current, not direct current like from these batteries, but I'll show you guys more on that here in a minute. Right? These power lines might be like, for example, 100,000 volts, just making up something. Right? But the current is really small. Right? It's more efficient to transmit electricity this way. And then you can use a transformer, and transformer will easily step up and step down the voltage and the current from alternating current. So you put a transformer here, have a huge number of coils on this side, have a small number of coils on this side. I'm trying to draw coils here, that's what it does. Okay? Step down the voltage from, say, 100,000 volts to, do you guys know how many volts are in these outlets in this room? How many volts right there? It's about 120 volts, right? Now that depends on what country you're in. So whatever country you're in, you have some standard, right? All over North America, we're using 120 volts. If you go over to Europe, you're on 240 volts. Actually, there's a couple of applications of 240 volts in the States. Like I think your washing machine uses 240 volts, right? But typically 120 in these outlets. Right? So you want to step down the voltage to make that work. Right? And last one I have queued up here is three-phase alternating current. So again, alternating current is different than direct current. Anything from a battery is direct current. There's a physical flow. Thank you. There's a physical flow of electrons from the negative to the positive lead, right? That flow around. Okay? But alternating current works differently. So alternating current, here's how you might generate it: is this magnet is hooked to a turbine, and so the turbine spins, that spins the magnet. Okay? That forces the magnet past these inductor type wires, okay? Which will generate a voltage, blah blah. Okay? And that alternating current, the electrons, there's no net movement of the electrons. They just switch back and forth, back and forth. You guys see three pairs of inductors. There's the green pair, the red pair, and the gold pair. You see those, right? They're connected in a loop, right? So there's like one green wire, one red wire, and one gold wire. So as the poles of these magnets swing by, they're moving the electrons inside, creating a voltage, but the electrons just move back and forth, back and forth, back and forth. There's no net movement of electrons in alternating current. Right? Now, if you look at the voltage as a function of time for each of these, it goes like up, down, up, down, up, down. Right? And you want three phases because if you just had one phase, then the voltage at some points would go to zero. So it would be like your electricity would be turning off. So, okay, well, if we had more phases, then we can kind of negate that effect, make it more constant, sort of, right? But then the trade-off with having more and more phases is that's more and more materials to build it. So kind of the trade-off is they went ahead and go with three. Right? So you guys, we went through 120 volts. So you guys know we have 120 volts here. Well, okay, I mean, it probably generates at like hundreds of thousands of volts, but you guys get the idea. There's some number of voltage. But what about this? I bet there's got to be some associated frequency. You guys think associated frequency? And if something's plugged into alternating current and you have a device that isn't ready to accept whatever frequency, like that would be bad. The plans wouldn't work. So every country also has to have a frequency standard. Does anybody know what the frequency standard is in the States? It's oh yeah, 60 hertz. Boom, there it is, 60 hertz. So 60 times per second this oscillates. Well, each one of these, right? 60 hertz, right? And then over in Europe, it's like 50 hertz. But all right, so you guys got that? All right, as a quick crash course of that. All right, so you guys have this page on your desk. Let's do some of these. I'm not gonna have you guys turn this in, but just keep this as notes. I'll give you guys some points in the gradebook for doing this, but just at your desk. Right, so let's do. I try to stick to some simple ones first. Okay? If you have a voltage source and a resistor, the resistance for that entire circuit is the resistance of that single resistor. So does that look like 3 ohms? Do you guys think 3 ohms in that case? Right. If you see, let's jump down to this one. You guys see 3 resistors in series. So the total resistance, you just very simply add up the resistors. So 7 to 10, 17 plus 11, it's like 28. You guys see 28 ohms total resistance. Is that? Let me break out my. Oh well, you guys see some posters hanging above my head anyway, but for the video, we've just been applying this one so far. So resistors and series, you just very simply add them up. Right? But at some point, we got to look at this. What if they're in parallel? Right? You can do this. Okay. Let's look at one of those. So one right beneath it, number 4. You guys see 2 resistors in parallel? Okay. Now in parallel, we're going to treat this as the same math as like 2 guys painting a fence, right? So one guy takes 7 hours to paint the fence, the other guy takes 10 hours to paint the fence. They make a 2-man team, as long as it takes them to paint the fence. Okay. So here, you can either do 1/7 plus 1/10, and then take the reciprocal of that and get 4.12 ohms. That's 4.12 ohms. Right? Or since there's only 2 of them, you could do product over sum. So you could do 7 times 10 over 7 plus 10, and it's the same thing. Okay, guys see it's the same thing? Product over sum. Guys see there? Right. Let's look at about number. Let's see what I got. Yeah, I would like to wire some of these up for you guys too. Here, I'll wire up number 7 for you guys. Let's look at number 7. Okay, so here's number 7 wired up. You guys see that? See, these 2 guys out here are in series with each other, but they're collectively in parallel with this guy, which is R3. You guys see that? Okay, this is what it looks like. You guys see that R3 is really bright and R1, R2 are really dim? Okay. Now, part of that has to do with the fact these are all the same resistance. All these bulbs are, but right. So one way to think of it is the bright one is getting the full 5 volts across it. And the dim ones, well, they're each getting 2.5 volts. This guy gets 2.5 volts. This guy gets the other 2.5 volts, right? And then you step back to Ohm's law and you can figure out the current going through. Okay. So what's the total resistance of number 7? Right now, there's a process with these, because right? Now these are starting to get more complicated. The process always goes like this: you find your voltage source, you fly over to the opposite side of the circuit, and you start finding equivalent resistances and work your way back towards the source. So the fact that these 2 guys are in series, what is that? That's 10 ohms and 7 ohms. That's like 17 ohms, right? So it's kind of like there's a single 17 ohm resistor there, okay? Back towards the source, we run into R3, which is 11 ohms. So this guy's 11 ohms, right? And now we can treat that in parallel. So we can do product over sum. We do product over sum. We do 17 times 11 over 17 plus 11, right? And that is 6.6 something, right? 6.68 ohms. You guys see that? All right, there we go. All right, let's jump down to, I want to do one of these down here. Let's do number, here, this one right here. There's actually a pair of questions. So what's the resistance? But then after that, what is the total current going through? Right, so you guys see R2 and R3 are furthest away from the source. So we're gonna start with those 2, R2, R3. Now those are in what? Series or parallel? Parallel, right? You guys see how the current has to split at that point and get pushed through both simultaneously? So R2 and R3, we're going to do product over sum, right? Which looks a lot like number 4, doesn't it? Just by itself. So product over sum of, so 1 and 2. So 1 times 2 divided by 1 plus 2, that's like 0.67 ohms, right? So then I'm going to go ahead and redraw the circuit. This is a good practice to do, is like redraw the circuit. So it's kind of like there's a single resistor here with an equivalent resistance of 0.67 ohms. Okay. R4 is still up here. That's 5 ohms. R1 is still over here. That's 1 ohm. And then there's the battery here. Okay. So now we're going to work back towards the source. These 2 guys, is that series or parallel? That's series, because whatever current gets on this road has to go through both sequentially, one after another. So you can very simply add this up. Is that like 5.67 ohms, you guys think? Okay. Then I'll redraw the circuit again, an equivalent circuit. Now, this 1 ohm I haven't touched yet, so he's still here. Okay. And this is like 5.67 ohms. Okay. Now those 2, is that series or parallel? Parallel. So I can do product over sum. 5 times, or so 5.67 times 1 over 5.67 plus 1, product over sum. So collectively, it's 0.85 ohms, 0.85 ohms. Right. Is that answer choice? Yeah, right there. Remember the analogy of like guys teaming up to paint a fence. This takes this guy 1 hour, this guy like 5 or 6 hours. They team up. It's going to take them less than an hour, won't it? So the resistance is always going to drop. Makes sense. The follow-up here is what is the current going, like supplied by the battery? Because the battery feels like it's pushing against a single. This is what the battery thinks. The battery thinks, oh, there's only one resistor out here, and it's 0.85 ohms. Okay, that's what this battery thinks is going on. Right, that's the total resistance it feels. Okay, so how much current flows? Well, if it's 5 volts, and I got 0.85 ohms, now we're going to break out Ohm's law. I equals V over R. That's Ohm's law. Voltage on resistance. More voltage, more current. More resistance, less current. Okay? That's Ohm's law. Ohm's law. Okay? So I got 5 volts on 0.85 ohms. That's 5 on 0.85. That's 5.88 amps. Okay? That many amps. Wait, hold on a minute. Did I round? Did we round a bit? We probably rounded, right? Right. Oh no, sorry, it's right there. It's right there. 5.88. Okay. Right. You guys get there? Good. All right. Oh, I'd like to. You know what? There are quite a few things I want to do with you guys tomorrow too. So, yeah. How about this? Let's save at least one of these waterfall models for tomorrow, and then I've got a few other demos signed up for you guys, and then yeah, really trying to condense a couple of weeks of stuff down to 2 days, but I think we're all right. I think we're on a pretty good pace here. Okay. So, who has any questions about anything from today so far?